Thank you. Right. So I'm going to talk about homomorphic encryption today, and its application in the blockchain. And so now it's time for smart contracts, right? And there is a vision behind it. It's the world computer. It's like the next stage of the blockchain, taking arbitrary pieces of code and executing them on a consensus network, and then reflecting that onto the ledger. It's a beautiful vision, but there are some challenges that we are aware of. One of the challenges, data I/O, simply just being able to feed arbitrary data from different places into the system. And then the second big challenge is how to ensure that these smart contracts are executed in a secure manner where the integrity is also preserved. And the nice thing is, just because of the fact that we're using these smart contracts and virtual machines that are executing via on the blockchain, right? On the blockchain, we already know that the integrity of the contract is ensured as long as the consensus protocol is sound. So that's kind of at least partially solved. There are efficiency issues, but they're being worked on. And I instead want to focus more on the privacy aspect of smart contracts. And currently, the way smart contracts execute, there is a lack of privacy in terms of the internals of the smart contracts. Any variable that is being executed, updated with arbitrary data, and then even fed into the blockchain, everything is out in the open. So anybody who's executing or mining smart contracts will see the data in open form. That prevents usage, right, in many different scenarios, such as financial applications and so on, where privacy is a serious concern. And there are essentially two ways where you can address this. And so one standard typical way to address this, where also there's some potential efficiency benefit, is actually employing some trusted execution environments. And essentially, you have an enclave running. It's enabled either via, on an Intel processor, let's say using SGX or ARM Trust Zone. And these enclaves give you some sense of security where you feed in encrypted variables into a trusted execution environment, and the results are then, encrypted and returned to you. So that's a great way. And then the second way that I want to focus more on in this talk is to use multi-party computing principles, and specifically homomorphic encryption. All right. So if you take a look very briefly into trusted execution environments, we have seen that 2018 has not been the best year for using enclaves or relying on them, because there have been so many microarchitectural attacks. And these are coming from basically very low-level hardware leakages. They are essentially caused by optimizations that have been built into microprocessor over the last 30+ years. And Intel and ARM and other companies, AMDs and so on, they have been innovating and essentially trying to save every little cycle, right, on their processors. So tons and tons of optimizations. And what that does, right, is you have fairly complicated architectures such as these. You have multiple cores sharing memory interface, buses, connectors, network I/O, and so on. And with this sharing, right, if you have sandboxing applied to it, you will still leak information inadvertently. And what that does is, we end up with attacks, powerful attacks, such as Meltdown and Spectre. And there are tons of variations to these attacks. It gives us a rich tool set as an attacker. So that's one of the things that I do, homomorphic encryption and microarchitecture attacks. And what happened is, in the last 10 years, these attacks have become very, very powerful, and to the point where you can actually now figure out what a micro operation inside the microcontroller core is executed. It's way beyond simple cache lines, which is what it used to be 10 years ago. And there are tons of leakages, and not all of them are published or turned into full-fledged attacks yet. So trusted execution is one way to ensure smart contract privacy, but they have sort of had a bad year. It's going to take some time for these problems to be worked out. It's not certain. So in the meantime, what we can do is we can actually think about alternative solutions that are coming from cryptography. And crypto gives you these beautiful, but heavyweight tools, really robust, strong tools that allow you to do secure distributed computation. So multi-party computing, MPC, right, is the buzzword for that, the general area. And one specific, the least interactive version of multi-party computing is where you can do homomorphic encryption. Essentially what that allows you to do is, it allows us to outsource computations to a semi-trusted server. Let's assume you want to do some operations on data. What you can do today is, let's assume you upload it to the cloud, right? Either you upload it in open form, so that means you have to trust the cloud service provider and assume they're keeping their system up to date and with security patches and everything, or you can encrypt them and upload them. But with current encryption, the way it's deployed is we encrypt and that's it. You can't do anything else, and then you have to download your data, let's say to search for a string in a file, or to do any computation. Let's assume it's an SQL query on a database and so on. With homomorphic encryption, it gives you an additional evaluation function that a semi-trusted cloud server can run for you without having access to the data internals. It gives you the perfect blinding mechanism so that the data, different kinds of queries can be run by the request of a client by the cloud service provider in a blinded fashion. They don't see the data, the inputs and the output results. They just send it in encrypted form back, and then decryption takes place on the client side, giving you end-to-end security. So it looks like this is a beautiful technology, right? It's the perfect solution, right, on face value at least, to bring privacy into smart contracts, right? If you use homomorphic encryption, and you could essentially anonymize or ensure the privacy of all the data being executed inside dApps, right? Thereby enabling financial transactions and healthcare kind of applications and so on. So conceptually, it's the right solution. And more than that, what you can also do is, currently you're selling cycles, right, when you're executing a contract. And what you can do is you can actually start selling private cycles. So that's the other, sort of add-on benefit. Of course, there's a downside. They will require more gas, right, if you think in those terms. But on the other hand, you can also think of this as another opportunity to sell private cycles, which are more valuable. So I'm trying to make it work in the blockchain setting with smart contracts, and this is how I kind of translate it into blockchain lingo, let's say. Now, if you look at it more deeply, there have been some work done at the blockchain level, for proof of work, right, versus proof of useful work. I mean, what can be more useful than doing, private computation? And it's a natural problem. It's a generic problem to solve. And if you do that, of course, it's much more valuable than, restricted applications that have been proposed in the past. All right, so that's how it looks like. Let's zoom into homomorphic encryption and what it provides to us. So it's perfect for smart contracts. You can feed encrypted data into smart contract, have it blindly executed, get the result out, put it on the ledger. And in terms of practicality now, there are two main types of homomorphic encryption. The stuff we had before 2018, which was all what we call partial homomorphic encryption. Payet, Benola, Goldwasser, Mikali, BGN, and are some of the examples of those. These are fairly efficient schemes that have been proposed in the past, primarily, brought in from public key cryptography. They are extremely mature and fast. The problem is their computation ability is fairly limited. You can do like simple additions or multiplications, or at best inner products and true in the BGN case. If you want to do arbitrary computation like we want to do in smart contracts, you have to use something more powerful, and that is what we call fully homomorphic encryption, or FHE. It's powerful. You can do arbitrary computations, but it's very slow. That's the biggest problem that we have now. There are two types of FHEs, leveled versus bootstrapped. Bootstrap means you evaluate things at the gate level. You can evaluate as long as you want. Leveled just means you can only evaluate certain functions that you know ahead of time at the time of encryption. So it's, again, a more restricted form. An added benefit of using homomorphic encryption is you have most of the FHE, well, pretty much all of the FHE constructions out there that I'm aware of are based on lattice problems, such as LEE, or coding-based, which is also can be reduced to a lattice, or N-truths by definition based on a lattice. That means they are quantum secure as far as we know it. And so there's actually a NIST post-quantum effort now going on trying to standardize some of these schemes, not FHE schemes, but other simpler kind of lattice-based constructions with lesser ability, signatures and encryption and so on. So that's kind of in the line of the change of what's happening with cryptography. With the emergence of quantum computers, we are moving away from RSA, we are moving away from ECC, from the traditional sort of public key schemes. And FHE fits very nicely into this because it's already post-quantum, because it's using that kind of setup. And finally, there is a standardization effort now happening with an open organization with participants from industry and academia, homomorphicencryption.org. You can see white papers there. And this year we had the third annual workshop. We're trying to discuss and come to a definition of a unified interface so that different libraries can interoperate. And talking of libraries, there are two types of libraries. Ones that are coming from companies. IBM Research has the very mature library now. HELib has been developed for many years. Microsoft has put out Seal, also a fairly capable library now. And we have just this year, Intel announced what they call an HE transform that automates automatic translation of AI models into a form that can be homomorphically or blindly evaluated. Very exciting news, and it's supposed to integrate with HELib and Seal. And on the academic side, we have TFHE, a bootstrap library, fairly complicated math, very involved, and WPI, so that's now my team. We have taken TFHE and some other libraries as well, and we have been for a number of years now, 7 or 8 years, have been working on these schemes, trying to accelerate them, because that's the biggest problem. And our specialty is putting them on GPUs. And we have a couple of libraries there, QFHE and CUHE. And we have also Python wrappers, so we're trying to make it more accessible to end users. And finally, we're working on a recompiler that takes regular Python code and puts it into a form that you can actually evaluate homomorphically. It will bind with QFHE. And there are some other libraries. The NGIT team, along with Galois, they have a library where they put a wrapper around HELib and Seal, and they're also working on other extensions. I just heard that they're working on bootstrapping now. And last but not least, it's not in the slides, but new FHE, right, New Cipher has their own version now, more commercial and more directed through smart contracts. All right, so there are problems in deploying FHE. It's not all a rosy picture. The biggest problem by far is still performance. Still fairly slow. And if you're doing shallow evaluation, just a few levels of logic, simple additions, and that restricts the application, right? Or simple few levels of multiplications. Then you can use partial homomorphic encryption. It's pretty fast. Footprints are small. Your operands are small, a few thousand kilobits. Alternatively, you have to use FHE, sorry. And if you're using FHE, there are two types. You can do leveled or bootstrap. Level tends to be faster. Things are more defined at a word level. You're encrypting 32 or 16 bits at a time. And then you can do additions fast, multiplications fast. But as soon as you try to do comparisons, like here, right? Okay. Like on the right, you have if x equals y, the comparisons are then become very slow because you cannot easily test things. You need bit level access, but you have encrypted things in word version already. And the alternative is what we call bootstrapped. And in bootstrap, everything is defined in bits, so you can do anything. You can do additions, multiplications, tests. But the addition and multiplication or word level operations are fairly slow. So the x plus y or a plus b, c times d's are very slow. The comparison becomes trivial then and efficient. So trade-off. And then finally, if you have more complicated functions such as machine learning functions, if you want to do blind ML machine learning, or model evaluation, then you need support for these kinds of functions. These are examples of activation functions like tanh and softmax and so on, sigmoid. These are all approximated. You have to use numerical computation techniques to come up with a circuit that will efficiently evaluate this, and then evaluate that homomorphically. And that's really expensive because you have lots of nonlinear operations. So key management is a huge problem for deploying, that prevents deploying of homomorphic evaluation or encryption in smart contracts. It's often overlooked. Everybody pushes that aside. But especially in the context of blockchain, where you're trying to save every byte, right, in these consensus protocols, the networking aspect is very powerful. If you're dealing with large keys like the ones in FHE, for example, in bootstrapping, if you're doing bootstrapping, then you need keys that are evaluation keys that are, and bootstrapping keys in the megabytes, tens of megabytes, 20 to 60 megabytes. Okay, that's per encrypted user, or user that contributes an encrypted piece of data. And if it's leveled, then it depends on the level of the computation. What's the depth of your evaluations? If you're doing 10 multiplications one after another, for example, right? Then 4 or 5 levels, that's what you need at least, and your keys will scale similarly in the megabytes with that. Tens to hundreds of megabytes. So that will be a major issue in deploying homomorphic or fully homomorphic encryption in smart contracts. Another problem, which is even more complicated, arises when you have multiple data sinks. You want to do computation, and multiple parties contribute encrypted data, and we want the end result to be shared by these parties back. That's sort of the generic multi-party setting. Then you need to be able to handle multi-key homomorphisms, and that means you need fairly sophisticated FHE schemes, and your keys will become even larger. It will become a key management nightmare. The good news is if you have only a single data sink, because of all of these schemes being public key cryptography, they can all be used, single encryption, right? You can just encrypt all the data with the public key of the person who's going to decrypt the result. In that case, this problem goes away. You fall back to the original, single key setting. All right, so one more problem is just interfacing. By definition, FHE is a little bit weird. We don't talk about functions being evaluated. We talk about circuits being evaluated. Circuits. So what you need to do, you need to translate regular pieces of code into a circuit and then run the evaluation function on it. And if you have, let's say, a piece of code like the if statement on the left, you need to translate it into a circuit like the ones on the right. One thing you cannot do is you cannot take shortcuts. If, let's say, X and Y are encrypted, or if any one of those are encrypted, the condition is encrypted. So you're doing conditional evaluation, but you don't know what the condition is. It's blinded, right? So what you do is you sort of compute both branches, all the assignment in both branches, and combine them by using a selector with this condition. And that's what you get here. So no shortcuts, all branches are evaluated, and that needs to be handled. And sometimes, if you're looping, for example, if your loop iterations are also in encrypted form, you don't even know when to stop, right? So that's something you cannot handle, and you have to throw an exception. So there is some management to be done here, right? And that means that we need new algorithms here, and also, ideally, what we need is something like a homomorphic cross-compiler that takes regular functions, where you mark up which of these variables are in encrypted form, and it automatically translates it into the circuit form. In my group, we have a project going on as exactly doing that, where you will be able to feed in Python code, and the output will be just the circuitized or arithmetized version of the same code. Functionally equivalent, but it will give us quite a bit of ease in terms of deploying these. All right, so conclusions. So there are lots of issues with trusted execution environments that prevent us immediate deployment in the blockchain, and same goes for FHE. TEs have to mature, right, because of all the hardware attacks. It's going to take quite a number of years until that happens. And FHE has issues that we just discussed, right? Now, so it should be seen more or less as a work in progress. Just practically speaking, These are both beautiful technologies, but they have not come to the point where they are ready for deployment yet. Now, that said, we will probably have a hybrid of these two technologies of some sort in a more restrictive setting. Let's say for certain types of computations, for let's say certain types of financial transactions, or for certain operations in healthcare databases. That we can do today with the current technology that we have, where we optimize these for very small evaluations, and that we can actually do today. Okay? So that's what I envision in the short term to happen. So what we need for full-fledged, robust, fully homomorphic, with arbitrary contracts to be deployed, for that we need to rethink and have more fundamental changes in the way we define blockchains or smart contracts, or have a breakthrough in FHE. So that's it. Thank you.